Okay, so today we are going to continue talking about hypothesis testing. We'll get through nearly every method you'll need in order to complete this Friday's homework assignment. We'll have one additional test we'll plan to work through on Wednesday, but otherwise you should all be good to go. And so we'll continue our discussion of one sample test of means. We'll start talking about two sample tests of means as well. And then a few deadlines. So one item I wanted to get some feedback from everyone. So I've reviewed all of your term paper topic ideas. And so I've highlighted my preferred topic, or the one that I think would be most feasible, knowing what I know about the topic and what data will be available. So those are covered in the last couple slides for today's lecture. And so what I want you to do in advance of Wednesday's class, so basically by close of business tomorrow, I want you to just upload a one slide overview of that topic. So I've created an assignment on D2L, and so you can just use basically this template and upload one slide, and we'll talk through those on Wednesday. So basically I'll look to get some interaction from each of you, and we'll talk through just thoughts on these various term paper topics. Beyond that, assignment one is due Friday, and then a week from Friday, we have an introduction section for our term paper will be due. And so we're basically alternating course assignments and term paper assignments every other week. So just as a big picture FYI, okay? All right, so at the end of today's class, you should be able to conduct a one sample test of means for cases where the variance is either known or unknown. And likewise, you should be able to conduct two sample tests of means, specifically for independent samples for cases where the variance is known or unknown with respect to those two samples, okay? All right, so previously we had introduced one sample test of means, and as you'll recall, for that specific application, we used the one sample z-test. Now, an explicit assumption in using the z-test versus alternate tests is that we know what the variance of the population is that we're studying. And what we tend to find in practice is that that's not going to be true because it tends to be prohibitively expensive for us to try to evaluate or collect data on an entire population. Typically, we are collecting information from a sample that's drawn from that broader population. Unfortunately, we don't have the capability typically due to practical reasons to evaluate the entire population. And so as a consequence of that, we've talked about this previously, we may tend to underestimate what the variance of the population is based on sample data. And so as a consequence of that, that's one of the reasons why we would use a different test for cases where that variance is not known to us. Okay. And so as we had just alluded to, in practice, the variance is often unknown and estimated based on a sample drawn from the population. And so in that circumstance, rather than conducting a z-test, we conduct what's referred to as a t-test. Now, you should hopefully have some familiarity with this from your prior statistical classes. But in any case, the two tests are largely analogous to one another. There are just some subtle differences that we'll talk through over the next few slides ultimately, okay? So the actual formula for a one sample test of means, assuming the variance is unknown, is simply that t is equal to x bar minus mu all divided by s over the square root of n. And in looking at this looks very, very similar in nature to what you've seen previously for the z-test. So in that case, essentially the only difference is instead of t, obviously we would see a z here, and rather than the sample standard deviation, we'd have the population standard deviation, sigma, in the denominator here, okay? And so just full definitions of those variables. So our t-test statistic is simply equal to the difference between our sample mean and some reference value of interest that could be the mean of a population, for example, under our null. And S is a sample standard deviation based upon our data. N is the sample size that corresponds to that sample mean and sample standard deviation, okay? So everything's virtually identical to what we've done in the case of the one sample Z. And the primary difference that comes into play here is when we try to select our critical value and determine whether or not we're going to reject, or if we fail to reject, the null hypothesis of interest. And so that distribution, rather than following a standard normal distribution, is going to follow a t-distribution. And so the t-distribution and most of the other distributions we'll talk about over the remainder of the semester, with the one big exception of the standard normal distribution, is going to be somewhat different in that the shape of these distributions are going to vary based upon the degrees of freedom that we have to work with, which is essentially they're going to vary based upon the sample size of the data that we're working with. And so to kind of illustrate this, this is a plot of some different t-distributions. And so each of these corresponds to a different number of degrees of freedom. And so for our intents and purposes, our degrees of freedom are going to increase as our sample size increases. And so as we look at the shape of this t-distribution, it tends to look very similar to another distribution that we're hopefully all familiar with. So can anybody in the chat box, what does that t-distribution look like in general terms? Anybody? Yeah, so it looks very similar to a normal distribution, right? And in fact, what we basically see, so with smaller degrees of freedom, it basically looks like a normal distribution with a lower peak and fatter tails. And so what that means in concept is that we have a higher number of extreme values as compared to the normal distribution. And as we increase our degrees of freedom, so the lowest distribution you see here in terms of the peak is for 1 degree of freedom. As we increase that to 10, you'll notice the peak gets higher, which means we're going to have more data points that are clustered around the mean. And as you'll see here, we have fewer extreme data points. And then as that approaches infinity, that basically is going to converge into a normal distribution, okay? So essentially, if we think about how this is set up, and think about how we would select critical values with respect to these distributions, we are going to operate under the same general principles we had used for the z-test, and that is we'd want to identify a critical value that would correspond to the most extreme 5% or 2.5% on each side if we were talking about a two-sided distribution. So we'd want to select critical values such that our likelihood of obtaining that extreme of a value, if the null is actually true, is less than or equal to 5% or 2.5% or 1% or whatever our particular significance level is, okay? And so what that means in consequence, if we think about our normal distribution, that bottom 5% is going to correspond to a critical value that's going to be smaller in magnitude than the t-distribution, because the t has fatter tails, and as a consequence, the top 5% of the normal distribution is going to include a percentage that's larger than 5% for those t-distributions. And so since we want to minimize that probability of committing a type 1 error, so it's no greater than, say, 5%, we would select a larger critical value as a consequence. And so what that means in practical terms is that in order to reject the null, we'd have to observe a larger test statistic for the t than we would for the z statistic, okay? Hopefully that makes sense. And so when we're looking at that uppermost tail, this is just basically showing us a representation of what those corresponding critical values are for the t-distribution based upon the number of degrees of freedom. And so when we talk about degrees of freedom, this is sometimes an unclear concept when we first start in this statistics. And so the number of degrees of freedom we have is basically telling us how many among our sample will have a certain number of observations that will be necessary in order to estimate these test statistics of interest. So in this case, in order to conduct a t-test, we would need to collect data for at least 2 observations, because we would need those 2 observations in order to estimate the sample standard deviation, for example, okay? And as we increase our sample size, first of all, we're getting greater confidence as to the estimates of our parameters here. But secondly, if we have a sample size of say 10 and we know 9 of those values, we would then, if we know the standard deviation, we would inherently also know the 10th of those values, because it could only take the one specific value if the other 9 are known to us, for example, okay? And so as we increase our number of degrees of freedom, or as we increase our sample size, like I said, this t-distribution is going to tend to converge towards normal. And if we think about those corresponding critical values as our sample size gets larger and our degrees of freedom get larger, and as we start approaching this shorter, flatter distribution, as we move towards the more peaked normal distribution, those critical values are going to be shifted inward, and they're going to tend to get smaller and smaller, okay? In the most extreme case, as our degrees of freedom approach infinity, if we go down to the bottom here, you'll notice that top 5% corresponds to the same 1.645 value we had introduced previously. Likewise, if we were conducting a 2-sample test, we'd be looking at plus or minus 1.96. And so as our sample sizes get smaller, what's happening is that we're increasing the magnitude of those test statistics. We're pushing those critical values further out into the tails, okay? And so in the most extreme case, if we have a sample size of only 2 observations, or we have just the 1 degree of freedom, we would then need a test statistic as large as 6.3 versus the 1.645, which means from a practical perspective, we'd need significantly greater evidence based on our sample data that there's a difference here, in order to conclude that that extreme of a difference isn't due just purely to chance, okay? So hopefully that makes sense. And so what we're going to do now, we're going to circle back to the motorcycle helmet law example that we had talked about in previous lectures. And so we had indicated in the past that our parameter of interest that we were comparing to, so prior to the helmet law being weakened, we averaged 106.5 fatalities per year. And that was over the 4-year period from 2008 to 2011. So the 4 years leading into that change. And so what we're going to do now, just like we had done with the 1-sample z-test, we're going to conduct a 1-sample t-test to assess whether or not that helmet law change had a substantive impact on motorcycle fatalities, okay? So the summary data is shown here on the right. We can calculate those sample values of interest. And so our sample mean, just summing the fatalities over the 6-year period and then dividing by 6, gives us 122.67. And then likewise, if we calculate the standard deviation of those quantities, so we're taking each of those individual observations, subtracting off 122.67, squaring those terms, summing them, and then dividing by n minus 1, so 6 minus 1, or 5 in this case, and taking the square root. And so that gives us S of 12.96. And you may or may not recall, this is larger than the population variance that had corresponded to this 4-year period that was presented to you previously. But the sample means the exact same in this case, okay? And so when we plug those into our test statistic, we'll find now that our calculated t statistic is 3.06, okay? And so that's our calculated value. We then need to determine what our critical value is that we're going to compare that test statistic to. And so we're going to denote that critical t value, or t sub c for critical, as just as we had done in the case of the z-test. That's going to correspond to the t value that establishes a specific probability of alpha, and we're going to use our traditional 0.05 value here. And so we're going to determine then, based upon our sample size and our corresponding degrees of freedom, the critical value from this table that corresponds to our significance level of interest, alpha, okay? And so if we were conducting a one-tailed test here, so as in this case, we're presuming that after that law is weakened, fatalities will go up. And so we'd be interested in one side of that specific distribution. And so in this case, if we have a sample size of 6 and we have n minus 1 or 5 degrees of freedom associated with that test statistic, we would be comparing to the critical of 2.015. And in this case, our calculated value is significantly greater than the critical. And as a consequence of that, we're going to reject the null hypothesis. And we'll claim, based on this data we have available to us, that our fatalities have in fact gone up as a consequence of that helmet law change. Okay. All right. And as we keep walking through this, feel free to type into the chat box should you have any questions, but hopefully that makes sense. It's just straightforward and very analogous to what we've done previously with the z-test. The only fundamental difference here is that we need to determine our degrees of freedom and then select the appropriate value from the corresponding columns here. Now, had we done this as a two-sided test, so maybe we didn't know going into this policy evaluation whether fatalities would go up or down, we would be concerned with either extreme of that distribution. So we'd be looking at plus or minus 0.025, so that 2.571 value in either extreme. Or if for some reason we thought fatalities would go down, we would be looking at the bottom side of this distribution. And just like the normal distribution, the t is symmetric. So in that case, we would just be looking as to whether or not our calculated statistic was less than negative 2.015. Okay. All right, and so as we look at a comparison between the one sample Z and t-tests, the calculations from our last few lectures are identical. The only difference here just relates to our population versus sample standard deviation. So it was 9.2 in the prior case, 12.96 when we use the post-helmet law data. Now that's, frankly speaking, just an artifact of the data. There's no inherent reason we would have expected the variance to be larger necessarily in the after period. We could have seen that it was smaller as a consequence. But if they were the exact same, this test statistics here would have given us the same result. And the only distinguishing factor then would have been whatever critical value we had selected. And so the smaller our sample size, the more extreme that difference is going to be between whatever's taken from the standard normal and whatever we see from the t distribution, okay? But functionally, you calculate the test in the exact same manner. We compare to critical values in a very analogous manner as well, okay? All right, now a related question that we're often interested in is, rather than comparing the mean from one sample to some arbitrary reference value of interest or some known population parameter, oftentimes we're in a situation where we'd like to compare the means between two samples. Typically, we do that to determine if there's a significant influence or significant relationship with respect to some parameter of interest that would distinguish that one sample from the other, okay? And so in these cases, you'll notice in terms of how we formulate the hypotheses, the null hypothesis in this case would be mu1 is equal to mu2. So that's just like the prior, in the case of the one sample test of means, we'd just be testing whether or not mu was equal to some arbitrary mean value mu naught. And so in this case, we're just operating under the null assumption that those means are equal to one another. And then depending upon how the problem is set up that we're investigating, we'd be concerned with either a two-sided or a one-sided test in terms of what direction that difference would be, okay? And so if we continue thinking about the helmet law example, let's assume that the pre-change data, so when the universal helmet law was still in place, so that'll be sample 1, and sample 2 will be the post law, so when we have the weakened secondary helmet use law, that'll be mu2, okay? And I introduced that in part because that will also give us somewhat of a different setup for these statistical tests, because if that's how we've defined our respective samples or populations from which those samples are drawn, instead of assuming, as we had in the prior case, that our sample statistic would generate a number of fatalities that was greater than the reference value, in this case, our a priori assumption is that fatalities are going to go up. And so we would basically be assessing this last one-sided hypothesis here, where alternative hypothesis is that mu1 is less than mu2, okay? Now keep in mind here, the setup is entirely arbitrary. We could have set this up so that mu1 corresponded to the post-helmet law data and mu2 corresponded to the pre-helmet law data. But just keep that in mind as you're determining your test statistic and your critical values, etc. Okay? All right, and so as we saw in the one sample test of means, in the two sample test of means, our decision as to whether or not to use a z-test or a t-test is going to be based on whether or not we know what the true variance of those populations are that we're comparing. So in this case, if we know what the variance in the number of fatalities is from year to year, now, just practically speaking, we don't know that. We're going to estimate that based on sample data for however many years of data we have available to us. But if we did know what the actual variances were, we would test them with this test statistic we see right here, okay? And so what we're doing basically is we're setting up the z-test so that we're comparing the difference between those respective sample means. So we can take the mean number of fatalities before the helmet law change, subtract off the mean number of fatalities after the helmet law change. And we're assessing whether or not that difference between those sample statistics is different than some arbitrary difference in those population parameters. Now, in nearly all cases that we would encounter in a practical setting, we'd just be interested in testing whether or not this difference was significantly different from zero. Okay, so whether there's a difference at all between those two population means. And so this term would be zero then, and that would basically drop out. And our test statistic would just be x1 bar minus x2 bar all over the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, where these are the variances and sample sizes that correspond to those respective samples of interest, okay? And so we would calculate our test statistic, compare it to the critical value from this table exactly as we would in the one sample test. Now, some real quick background here. So we've introduced previously this bottom term here is going to basically be the standard error of this topmost term. And so it should follow, if you just kind of think through what we had talked about for the one sample test, the standard error for the mean of a sample was just sigma divided by the square root of n, right? And it turns out if we go back to just the fundamental theories of probability, we'll find if we take one normally distributed random variable and we subtract off another normally distributed random variable, our mean is expected to just be the difference in the means of those individual populations or samples, as the case may be. And the variances are actually additive. Okay, so if whether we're taking the parameter from one population and adding it to another randomly distributed variable, or if we're subtracting the means between two samples, those variance terms are going to be additive. So we take the variance of the first sample plus the variance of the second sample plus the covariance between those two samples. Now, since we're assuming these tests are independent of one another, that term drops out. And so that's why in the denominator here, we just see the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, okay? Now, this is going to be about the only extent to which I'm going to talk about this test within the context of this class, because we never we rarely will use this in practice because generally speaking, neither of these variances are going to be known to us. So instead of the two sample Z, we use one of two different formulations of what's known as a two sample t-test. And the most widely used of those t-tests was developed by a researcher with the pen name of Student, who happened to work for Guinness Breweries back in the day. So this had to relate to manufacturing and distribution at a distillery. And so since the population variants are generally not known to us, rather than using the Z statistic, we're going to use the T statistic, okay? And when we conduct these t-tests between two independent samples, we also need to take into consideration whether the variances of those two samples or the two populations from which they're drawn are equal to one another. If they are equal or essentially equal, then students' t-test would be appropriate for us to use. And so students' t-test is as illustrated here. Now, one quick point of note here. So the setup here is exactly as we had seen previously. So we've taken our sample means x1 bar minus x2 bar. We're taking the difference between that sample quantity and some hypothesized difference in the population means of interest. So again, in this case, we're just testing whether there's a difference. So whether the difference between these sample means is different than 0. So that term is going to drop out of our subsequent calculations. And then the denominator looks very similar, except rather than having s squared over n1, sorry, s1 squared over n1 and s2 squared over n2, we have sp squared, where the p stands for pooled. So this is our pooled variance, and that basically is just telling us that's an average variance across those two samples. So in concept, it's as if, you know, S1 is equal to S2 is equal to SP. And so both of these would be SP squared. It's analogous to saying SP1 and SP2 because we're operating under the S1 squared and S2 squared because we're operating under the assumption here that those variances are equal to one another when we're running students' t-test, okay? Now, as you'll recall, in the one sample test of means, our degrees of freedom associated with that test was equal to n minus 1. Now, in this case, we have two different samples we're comparing to one another. Each of those samples has degrees of freedom that are equal to n minus 1 for those respective samples. So as an example, we would need to have at least 2 observations in each of those individual samples in order to calculate a variance and to ultimately calculate this t statistic. And so we have n1 minus 1 and n2 minus 1 degrees of freedom for samples 1 and 2 respectively. And so just adding those quantities together is where we get the n1 plus n2 minus 2, okay? And as we had before, we would compare these t statistics to the associated critical values in this table that correspond to our significance level of interest, okay? All right, and again, if the variances are assumed to be equal, we calculate that pooled variance as just a weighted average of samples N1 and N2. And so if it's not obvious from first glance, all this is showing us basically is that we're giving greater weight to the variance that's associated with a larger sample size, okay? And so that should make sense if you have two samples and one of those samples has a sample size of 100, the other has a sample size of 10. We would give more weight towards that one that has a sample size of 100 as an example, okay? And so calculation of this then is just basically a straight weighted average of the sizes of those samples times their corresponding sample variances, okay? And so we'll return back to the data we've been working with over the past few lectures. Now, up to this point, I had only shown you the detailed information for the latter 6-year period after that helmet law change had occurred. And so at this point, we're also introducing similar data for the 6 years that immediately preceded that helmet law change going into effect, okay? And so starting first of all with the pre-law change, so from 2006 to 2011, we want to calculate our sample means and variances or standard deviations for these fatality statistics. And so X1 bar during the before period prior to the change is going to be equal to 104.17. And again, that's fatalities per year. The associated standard deviation, just taking the difference of each of these from 104.17, squaring, summing, and then dividing by n-1 or 5 in this case, would give us a sample standard deviation of 8.4. Okay. And moving on to the second case here for the post helmet law change period, we've already calculated these statistics previously, so these should look very similar to you. Our sample mean after the helmet law was weakened was 122.67, and the corresponding standard deviation is 12.96. Okay. And so from that, we can plug those values from the two preceding slides directly into students T. And so our pooled variance, keep in mind our samples in each of these cases were 6. So we have n-1 or 5 times our sample variances. Now, one real quick point of note here, keep in mind we're using this to calculate a weighted average of the sample variances, not the sample standard deviations. So I need to be sure to reinforce that SP is not a weighted average of S1 and S2. So we would calculate the pooled variance, and then we would take the square root of this quantity in order to determine the pooled standard deviation. So I just want to make sure that point is crystal clear for everyone. And so going through these calculations, we'll find that our pooled variance is equal to 119.22. And so we could take the square root of that quantity, and we'll basically find that would put us between the 8.4 and the 12.96. Okay. And so we take that pooled variance, we plug that into our t-statistic calculation, and just restating the information from before. So before the helmet law change went into effect, we had 104 fatalities per year roughly. That increased to 122.67 afterwards. We're testing whether or not this difference in traffic fatalities is significantly different from 0. And so that 0 term is just dropped out here. We've plugged in our pooled variance to the denominator, and our calculated t-statistic is negative 2.93. And now I'll reinforce the prior discussion we had about which we arbitrarily assign as sample 1 versus sample 2. So in this case, we had presumed that fatalities would go up, and that would be associated with a relatively small, in absolute terms here, test statistic. And so we're going to compare that negative 2.93 to the bottom 5% of that t distribution. Okay. And so in this case, selecting that critical t value, keep in mind, in this case, our degrees of freedom are n1 plus n2 minus 2. So 6 plus 6 is 12, minus 2 is 10. And if we're conducting a one-sided test, so we're interested only in that bottommost tail, in going to our table here, our critical value is 1.812. Now keep in mind that corresponds to the top 5%. And so the bottom 5% is just the negative of that quantity. So negative 1.812 would correspond to the bottom 5% with 10 degrees of freedom. And we'll see that the top 5% again corresponds to positive 1.812. In this case, we're interested with that lower 5%. And so we compare our calculated value of negative 2.93 to negative 1.812. Since we're beyond that critical value, so we're far off in the negative in the lower tail past that corresponding critical value of 1.812, we can reject the null and hence claim that we do see a statistically significant difference in the fatality rates. And it appears, based on the evidence we have available to us, that fatalities have increased, coinciding with that weakening of the helmet law. Okay. All right, and so that's students' test, and as we had noted, that's appropriate when the variances are equal between our two samples. Um, when those variances are not equal to one another, then instead of using students' test, we use what's referred to as Welch's t-test, and this will look very similar to what we've seen previously. And so this actually looks more similar than the two sample z-test than students tested. So the setup's the exact same, the numerator's identical. So we're just taking the difference between the means of samples 1 and 2. We're comparing those to some hypothetical difference of interest between those population parameters, 0 again in this case. And the denominator is actually the exact same as we would see in the z-test. So rather than pulling out the variance, which is pooled, we're treating each variance separately here because we're operating under the assumption that those sample variances and the population variances that correspond to the populations from which those samples are drawn are not equal to one another, okay? And so the part that's somewhat different here in terms of assessing this is since the variances of those two populations or the two samples are different from one another, it's not as straightforward to determine what our corresponding degrees of freedom are in this case. So it's not just going to be n1 plus n2 minus 2. That's going to basically be the limiting value as our variances get closer and closer to one another. When those variances are exactly equal to one another, our critical value will correspond to n1 plus n2 minus 2 degrees of freedom. But as those variants differ from one another, we'll actually take a weighted average between those respective quantities. Okay, so our degrees of freedom are calculated as shown in the formula that's illustrated here. Now, it may not be obvious at first glance, but all this calculation is doing is basically taking a weighted average based upon how large the difference between those variances are from one another, okay? And so as the variance of sample 1 relative to sample 2 gets very large or vice versa, what will tend to happen is that this will shrink down from that n1 plus n2 minus 2 quantity. And if those variances are equal to one another, then this will just simply reduce to n1 plus n2 minus 2, okay? Now, it might not be obvious at first glance why we're doing that, but the easiest way to demonstrate this is probably just by simply walking through the test statistics, okay? And so in the case of Welch's t-test, we've already gone through some of the intermediate calculations here. So we know our sample means are 104.17 and 122.67. And so our variances, which were calculated previously, are equal to 70.57 and 167.87. Now keep in mind, we had previously presented standard deviations rather than variances, so I just simply squared those terms here, divided by 6. And so in this case, our calculated t-statistic is negative 2.93. Now, if you keep in mind, that looks very similar to what we had worked through previously in the case of students' t. So the actual calculated t-statistic is not going to vary in this case. It's only going to be the degrees of freedom for our corresponding critical value. And we'll leave kind of the accompanying side discussion for some further thinking on your part as we move forward here. We can calculate our degrees of freedom here using the formula demonstrated previously. And so rather than seeing the maximum of 10 degrees of freedom that we could experience in this case, since those variances are relatively different from one another, so one's nearly twice as large as the other variance. In this case, our degrees of freedom have been shrunk down to 8.57, okay? Now, when we look at the critical values, we don't have an 8.57 here. And the whole reason why we're reducing our degrees of freedom, in short, is because our sample variances we've determined are not equal to one another. And since they're not equal to one another, from a practical perspective, we have a bit of a concern here, because let's say one variance is significantly smaller than the other. One potential implication there is that we could underestimate the variance of that difference, and what that would mean in a practical sense is that the denominator for our t-test may be smaller than perhaps it should be. And so as a consequence of that, we want to be a little bit more conservative and establish a higher threshold value that would correspond to us rejecting the null hypothesis, okay? And so in this case, what we're going to do, since we're looking to be more conservative, there's not an 8.57. I mean, we could interpolate, but generally speaking, we just simply round down to the next integer. And so we would just take a critical value of t at 0.05 with 8 degrees of freedom is equal to 1.86. Now, in this case, keep in mind, we're concerned with only the lower tail because we're assuming going in that our test statistic will be negative. Okay, and so likewise, if we look at the top 5% of that distribution, that critical value would be 1.86. In this case, we're concerned only with the first of those two values. And so negative 2.93 is less than negative 1.86. And as a consequence of that, we can then reject our null hypothesis, okay? All right, now a few things to think about and maybe play around with some data as we work through these test statistics here. Think about under what circumstances we would get the same results in terms of the actual calculated t-statistics there, first of all, and then secondly, in consideration of our degrees of freedom that are associated with those tests. And as a part of that, it would be useful to look at what happens as the sample sizes diverge or converge away from or towards one another. So if you have one that's sample size at 10 versus 100, what happens as those samples get closer to one another? And then likewise, what happens as our sample variances get significantly larger or smaller relative to one another? Okay, so just a few things that we'll want to think about. Now, at this point, this wraps up the general content I have for today. So this should hopefully be a bit more in line with some of the typical lecture lengths in terms of new content moving forward. So we've got about 45 minutes worth of content there. There are a few additional items I wanted to touch on just real quickly. So as I had mentioned previously, all of you had provided term paper topic ideas. I've gone through and reviewed those, and I've attempted to select one of your 3 topic ideas, and I made that selection largely on the basis of whether or not I thought it was feasible to investigate, and then secondly, whether you would have a sufficient amount of data available to you. And so if your topic idea looks different from what you had initially proposed, that essentially means that I've modified it slightly based upon either concerns I have about the data or some knowledge I have to that end. And so I'd like you all to just kind of look at your topic that's been assigned here. And if you have questions, we've got quite a bit of extra time built into today's lecture, so we can walk through some of those questions over the remainder of the lecture period or into my office hours subsequently. But like I said, for Wednesday, I want each of you to submit by midnight tomorrow one slide that basically details the same 3 questions I had asked for each of these topic areas. So what are you going to investigate? What data are you going to use to conduct that investigation? And then what other factors of interest would be of use to you in conducting that analysis or investigation, okay? And so with that being said, I'm just gonna walk through these really quickly. So in the case of Folarin, he would be looking at the effectiveness of forward collision warning in automatic emergency braking systems. We have data available to us from the Insurance Institute for Highway Safety. And so I think there should be quite a bit of information there that we could do some interesting analyses to ascertain when vehicles tend to start reacting to potential rear-end collision scenarios more quickly. In Nishal Gupta's case, we have a significant amount of crash data as well as speed data that's been collected before and after some speed limit increases have occurred throughout the state. And so using the speed data to investigate the relationship between speed changes and crash risk, essentially. Similarly, Emma Hagel has some data available related to Michigan roundabouts, and so we would be interested in comparing roundabout safety performance to traditional signalizer stop controlled intersection configurations. And there's a few different directions we could go with that, including changes once specific locations were converted to roundabouts, as well as things like learning effects over time. There's several directions we could go there. Jordan Hankin has been evaluating driver assistance devices. So he actually presented in seminar last week. And so you may recall from that seminar discussion that there's a bunch of field data that can be used to assess when and where those driveway assistance devices tend to be most effective. I guess as a note to Jordan, there's also some companion survey data there that would be of interest as well. So I guess I would defer to Dr. Gates and you in part as to which of those would be more feasible in the near term. And then another study that Dr. Gates's group is doing right now relates to driver speed feedback signs on exit ramps from high-speed freeways where significant speed reductions are required to navigate the horizontal alignment of these exit ramps. And so in this case, essentially looking at how the effectiveness of those signs varies based on different site-specific factors or sign feedback related factors. Farish, yours is one that I think we have sufficient amount of information available there, but I have zero familiarity with the actual data that's available beyond what you had provided to me. And so I think that there's an opportunity to use the data that's reported on a regular basis regarding ferry systems across the US and trying to assess the performance of those systems from an economic viability standpoint versus some of the operational and service measures or characteristics that are collected as a part of those investigations. Okay, so that's one though you might want to meet with me offline or check which specific data are available there. And in each of these cases, I guess as a broad suggestion, our hope here is to develop multiple regression models, whether those are linear regression models or some other form, will remain to be seen here. But we'd want to identify at least one dependent variable of interest, and we'd want to identify multiple other variables that would be correlated and or predictive of that measure of interest. Okay, so whether that variable of interest is crashes or speeds or an economic indicator, we'd want to make sure we have several different variables that can be used for predictive purposes, essentially, or forecasting. Okay. The last group of students here, so Asan Tamjo has some data related to a collision avoidance and mitigation system that was installed on some MDOT snowplow trucks for some field tests that were conducted a few years ago. We have high definition, I believe, radar and potentially LiDAR data. So we've got information in short on vehicle trajectories. And so there is some potentially interesting insights we could gather from that. Now we will want to probably circle back and just verify that there's enough information there to develop some reliable models, because I know we have had some issues with QA, QC, and data quality with that specific data set. So just a quick note to ASON there. Emily Kauka, I would suggest we look at how travel levels have changed generally as a result of COVID-19. And so we have some baseline data and we can go about requesting some additional information that can be used for the purposes of a larger scale analysis. So that's probably what would be most feasible based on what I know today. Jonathan Kay has a bunch of data available that details the performance of median U-turn intersections. So basically intersections here in Michigan where we prohibit left turns on specific approaches and we instead require those vehicles to then turn right and conduct a U-turn in the median. And so there are several perspectives from which we could try to evaluate the safety performance of those types of intersections. Jesse Liu, you had a number of more general investigations of interest that talked about, it seemed like things like driver compliance or driver violations and things of that nature and how those would relate to safety performance. Now, we don't really have a robust database that details violation information that would be available selectively from law enforcement, but it's somewhat challenging for us to try to work with. So I would suggest instead that you examine how crash rates vary across different types of roadway locations. And so we could look at locations that are prone to certain types of errors or driver mistakes as an example, and sort of quantitatively compare risks across those different sites is probably the closest I could come based upon the information that was provided. And then Hamid Mosafari, so in your case, one of the suggestions or one of the topic areas was looking at the severity of crashes across different vehicle types. And so there are several different data sets we could use either nationally or here in Michigan to investigate that issue. So I think that's promising. Babak Safai, I was interested in the topic about road user feedback on autonomous vehicles. So you had indicated there were some publicly available data sets there. So I think it'd be good to work through some of those as well. And I guess just let me know. I just did a quick web search and found a few different freely available public data sets that could be used for those purposes. So I think that should be safe. And then lastly, Amirali Sultanpour, I suggest we look at what subsets of drivers are most prone to involvement in different types of crashes. So this was kind of a slight change in direction from what had been suggested initially, but I thought it would be interesting rather than comparing differences in single versus multi-vehicle crashes, for example, looking at what types of drivers are more likely to be involved in these different types of crashes, because that may give us some insights into differences in driving behavior, attention, risk, etc. So anyway, what we're looking for on Wednesday is just for all of you to flesh all this out in a little bit greater detail, and we'll go through one slide per person, just kind of talking through what you intend to investigate, and then we'll have an opportunity to get feedback from myself as well as from your classmates as to those respective topics. So if you have any questions in advance of Wednesday, I guess you need the slides to me by midnight tomorrow. So, feel free to check in with me later today or into tomorrow, but that's essentially what we're looking at. And so on Wednesday, we'll continue and we'll wrap up our 2-sample tests, at least parametric 2-sample tests. And a lot of that time will be allocated towards discussing the term paper topics. So keep in mind that slide is due by midnight tomorrow. The first assignment is due midnight Friday. And then later today, we'll also have details going up for the introduction section of your term papers, and that will be due next Friday, February 12th. So with that wraps up everything I had on my end.